Y, so it rotates around this axis and then around this axis. And that has some advantages. But most of the antennas we use in BLBI are this type. So you have someplace down here, you have something that controls the antenna and called an ACU, or antenna control unit. And we have software that connects to that tells where the antenna should point. And here is a chart of the electronics. And this is for a Vigo system. And we have some feed here. And the feed is sensitive to two polarizations, horizontal and vertical, or X pole and Y pole. This is different than in SS, where the feed is circularly polarized. So in the Vigo system, we have two signal chains. And we have an amplifier, a low noise amplifier for the X pole and a low noise amplifier for the Y pole. And then it goes down through all of these different parts. And this UDC stands for up-down convert. What this does is this converts a signal from the observing frequency, whatever it is, down to where it is sampled. So the signal is converted down to where it's sampled. And this RDBE, the RDBE stands for digital back-end. So that's the thing that samples the signal, and then here's a recorder. So that's one part of it. The other part here is some calibration equipment. This is that does the cable delay management system, and it's in the signal up to the antenna and back down. You can see everything here is time tagged with this hydrogen maser. And the hydrogen maser, the really expensive parts of this, the antenna is really expensive. The hydrogen maser is really expensive too. It's like $500,000 US.
Professor,
yes.
What's the minimum speed of making one Mark 6 units?
How fast can you record?
Yes.
I don't know the answer to that. I know that for if you want to record really high data rates, we can record two of them simultaneously. And here is how the light ray comes in. And the light comes in here. It's a plane wave. It hits the reflector, and then it goes up to the feed. Now, in the Bible, Jesus tells parables. At least that's the word we use in English. Do you use that same word in Portuguese?
Repeat, please.
Parable? But for a story that has a point. Do you know what I'm saying? So in the Bible, there are these stories that Jesus tells, and they have some sort of point, and that comes from the same meaning here. Is that?
O foco da parabólica, né?
Yeah, the parabola focuses things, and in a parable, that kind of story, you also focus things. So that's just interesting. So you have a parabola main reflector. Now, in a previous life, I used to measure antenna surfaces, and I used to go out and align the panels, and there's a rule of thumb that if the panels are misaligned by a 1/16th of a wavelength, you lose 50% of the power. So you have to have it be very precise when you're aligning these things. And since it goes like the wavelength, if you want to observe at higher frequencies, you have to have a more precise panels. It has to be smoother. So going back here, you have the feed, and the feed sees part of the antenna. And the part of the antenna that it sees is, it's called the illumination pattern. Imagine that you had a flashlight up at the feed. What part of the antenna does it light up? And ideally, what you'd like it to do is light up the antenna and not put any light elsewhere. Now, we're talking about radio waves here, but it's the same sort of principle. And here we illustrate three kinds of illumination pattern. One is over illumination, where you have a lot of the signal goes outside of the antenna, and that's not good. The other is under illumination, where you don't illuminate the outside very much. And then we have this sort of right kind of illumination you like, something like that. So here we're talking about sort of broadcasting, but if you're receiving, you have the same sort of thing.
Professor, this mainframe is needed to make the buffer construct the antenna. The mainframe is need calculated buffer constructs the antenna, right?
Can you? I'm not sure I understand the question.
This calc is need made before the making antenna or after this buffer, right?
Could you?
Yes. This set of calculation, the acquisition done before construction.
Yes. So, yeah, they're done before the construction, and in fact, when you build an antenna and have it designed, that's part of the design characteristics. Is you say, you know, how much illumination you want, etc. And the beam pattern of the antenna is that Fourier of the aperture illumination. The aperture illumination function is how much of it is sort of the strength of the signal across the antenna. And a rough estimate for these things is that the beam width is lambda over d. So that's sort of the resolution of the antenna, where lambda over d is measured in radians. And this is, beam width is where the signal drops down to 1/2. So there are different kinds of antennas. The first kind, the antenna that we saw, the simplest kind, is called a prime focus, where the signal comes, it bounces off the subreflector, and then it goes up to the feed. You can also have antennas which only have part of the surface there. There's still a parabola, but they only have part of the parabola. And I've sometimes seen these, if you look closely, you see people who are like TV newscasters, and they have mobile antennas. Sometimes there'll be an offset parabola to save space. Another kind of antenna is called a Cassegrain antenna. And here you have a primary reflector, and then you have a subreflector. And in the subreflector, so the beam hits the back of the antenna, goes up to the subreflector, goes in there, and the feed, the place where you receive it, is down there. And you also have another version of this where you have the shape of the subreflector is different. So the common types we normally use are Cassegrain and prime focus. There are some systems I've seen where this subreflector is semi-transparent. So it's transparent at one frequency, and you have two feeds. You have a feed down here and a feed up there.
Oh, you can filter the fragments, right?
Yes. So, and the reason for that, or one reason for that, is that it's difficult to have feeds that, it used to be difficult to have feeds that could observe at different frequencies. You had to design one feed for one frequency, one feed for another frequencies. And on some of these antennas, they used to have a lot of different feeds, and you rotate them in or out depending on what you're observing at. So there's this concept called aperture efficiency. And this is, ideally, you have the area of the antenna is a measure of how sensitive the antenna is. But you have various factors that cause that to diminish, depending on your illumination function. To illuminate the central part of the beam, then really you're not using all the antenna. So you have to multiply it down. So here there are, various formulas here for these factors, all of which are less than 1. one of the factors is that part of the signal is if I have a subreflector here, part of the signal coming in is blocked by that, so you don't see that. If I have legs that are holding up the antenna, part of the signal is blocked by that, so you have to take that out. So in any case, so you have this complicated formula here, and generally you like something that's above 50%. I'm not sure exactly what the specs are, FGO, but 50, 60, if you can get up there.
No problem if you
So here is a picture of what the feed looks like in essence, for Vigos. And it has this shape here. This particular feed was designed, I think, out at JPL, and it's called a feed. And it is sensitive to frequencies 2 to 14 gigahertz, which is the frequencies that we use at Vigos. This is a whole, the people whose profession is to design feeds. And here's a chart showing the sort of response of the feed at different frequencies, at different angles. Ideally, you'd like the feed to be sensitive to stuff that's right in front of this and not observe anything further out. So this is sort of the feed pattern. And the other thing you want is when the signal goes through the feed, it changes the phase of the signal. And it changes the phase as a function of frequency. And you'd like the phase change to be constant across the frequency that you're observing. So here it just shows what the phase change is. And this kind of measurement is made in a laboratory. So here is a picture of the feed. And you also have a picture of a LNA. Who knows what an LNA is? An LNA stands for a low noise amplifier. So this amplifies the signal without putting in a lot of noise. And to minimize thermal noise, both of these are cooled to under 20K. So I don't know if when we went out to the Fortaleza antenna, if they talked about the cryogenic system there, and they pipe liquid helium to keep everything cool. And so, we want everything to be really cold. Now, why is that? And the reason is that the radio sources we observe are very weak. Somebody once told me that if I had a cell phone on the moon, the cell phone would be the strongest signal I'd see in the sky, the Earth. So, the signals are just very, very weak, and to see them, we need to have very sensitive equipment. So here's just a picture showing, we saw part of this picture earlier. You have the feed, you have these two low noise amplifiers. And we talked about this earlier, but here's another schematic. We have the feed, we have this low noise amplifier, then the signal is down converted, then the signal is filtered to take out parts of the signal, and it's sampled. And here we have this hydrogen maser, we have this local oscillator there that controls the down conversion. In slang terms, people call that an LO. So if you see LO, that stands for local oscillator. And one of the things in the schedule file is it will tell you what those LO should be set to. And it will also tell you when you do the sampling, how you take the samples. So the signal goes through a couple of stages of amplification. And the main point here is that the first amplification is the most important. because each state of the application injects additional noise. You want to have a minimum amount of noise in the first application. So most of these slides, I'm just going to skip over very quickly or talk briefly about this. One of the concepts is what is the sort of intrinsic noise in the antenna? And that's called the antenna temperature. About measuring this. And here's a picture of the system in a duo. Okay. So I just wanted to go through this stuff so you guys got a picture of what the antennas look like and what some of the hardware looks like on this. This is an area, VLBI has people contributing in many, many areas, and this is one of the areas. And we need to have good electronics, good antennas up front so that our signal is good, so that we can do good things with it further back down. Okay. Jean-Pierre, would you like to give your talk now?
Posso ficar em pé? Tipo assim. Tem gente, se eu parar, vai parar.
Tem
Sim,
quantas
acabei de dar uma-
pessoas?
Acabei de dar uma- tem 13.
13. Então, só lembrando que a tarde é contrário. Claro, não haverá. Então, por favor, assista à tarde, porque haverá atividades. Depois do feedback, acho que os alunos vão apresentar o seu trabalho. Os trabalhos durante a semana. Aqui eu vou mostrar rapidamente, 10, 15 minutos, uma apresentação. Vocês não viram que nós estamos lá na UFESA, acho que era importante mostrar para vocês também. Aqui na cidade de Fortaleza, acho que é na UFESA. Beleza. Então, é rápido. Aqui, lembrei das pessoas que vêm do.
Quem vai inside here?
Você tem?
Tem antena. Cat tem antena.
Agora vai passar.
Vamos lá? Então, lembrando para vocês que chegam agora que a tarde não haverá nós estaremos aqui. E aproveito, antes de concluir, antes do Max apresentar os trabalhos sobre o europeu, na primeira apresentação, eu mostrei lá no FESA, mas vocês não veem, acho que é interessante, quando se trata do região. Ou é a mesma coisa, Fortaleza, tipo de negócio. Então, aí, lembrando aqui, então, aproveitando, a gente tem aqui os nomes dos que realmente operam no sistema VDI. Então, ele seja por aqui, eu digo aqui, Renato, Emerson, que é o acho que o nome dele é engenheiro.
Quem é engenheiro? Quem é engenheiro?
Um dos três, acho que eu
Falei que eu também engenheiro.
não, eu não sei. Um dos três, porque eu já nem nasci. Bom, lembrando que a área é áreas, e você vê aqui o prédio principal, a antena VPI, e tem também equipamentos, subestação elétrica, tem operação de magnetômetros para o campo magnético, geomagnético, isto é operado. E, finalmente, a noção da, como já comentamos, para fazer remote sensing da ionósfera, poder obter as camadas subcamadas dessa camada ionizada. Também operado do IP, lembrando que essa ionoção é a mais antiga, ainda é operação no Brasil. Os séries de campo, séries temporais muito valiosos. Tá? Okay. Bom, então, rapidamente, o acordo bilateral entre os Estados Unidos e o Brasil, feito através do acordo entre a NASA e a Agência de Pesquisa Brasileira, que é renovado, cada 10 anos, desde 90. E o último era de 21, estamos no período de transição, agosto de 21, 23. Então, agora novos parceiros, o IFCE, e pretendemos em breve renovar para mais 10. Mais em 2024. Isso inclui manutenção, inclui os engenheiros, inclui a manutenção, por exemplo, se o pessoal vai participar, é importante que o pessoal participe de reuniões técnicas das outras áreas, muito bom para eles e assim por diante. Bom? Bom, isso já falamos muito lá o princípio da radiointerferência é observar pontos pontuais para estabelecer esse cara aqui, que é o International Celestial Spring, e medir o ITRF através do EUP, o International Interferência, falamos também muito aqui, não é a Liga Técnica, são 3 SNRs, o 2, que é da França, e o GDS.
Excuse me, Professor. Please, for the camera.
Começou, isso daqui já. E, obviamente, a grande jogada daqui a pouco é transformar esse nome da superliga de Gibson, trocando esse D, diâmetro de uma antena, por D de separação entre duas antenas. Pode passar. Por favor. Bom, aqui há alguns exemplos que um mostrava hoje pelo rei, outro aluno de mestrado que já defendeu para a espacial, é a análise espectral dessa duração do dia, LOD, né? Aqui você vê o excesso com respeito a 24 horas, que são 400 segundos. Tá? Então, sobra, vamos ver aqui, alguns milissegundos, isso vai se acumulando. Então, a Terra gira menos rapidamente, acelera, desacelera, acelera, desacelera, acelera. Bom, aqui, tirando o trem, os efeitos de maré que eu explicou, a gente pode, por exemplo, essa curva tem um dos componentes do sinal, essa curva vermelha aqui, que não é nada mais que a curva azul aqui, que é o ciclo solar de 22 anos. Então, ciclo solar de 11 anos, mas, na verdade, de 11 em 11 anos, a polaridade magnética do polo muda, então você reencontra a mesma situação apenas 22 anos depois. Então, o ciclo magnético solar é de 22 anos. Então, isso poderia ser interpretado como interação do vento solar. O polo magnético, campo magnético polar com a atmosfera terrestre, e isso teria uma influência na velocidade da rotação. Outro resultado que, não sei se foi comentado, e aí a gente que fez uma decomposição. Também tirou, por exemplo, o resíduo que fica aqui mostrado em azul, comparado com uma característica do fenômeno de são 7 parámetros, e mostrado aqui em vermelho. Aqui a ideia é que os resíduos desse sinal são bastante bem correlacionados com as três eventos em nível. Uma aplicação, algumas aplicações do que pode ser feito com os dados, por exemplo, aqui do LOD, os dados estão disponíveis. Lembro que foi feita a troca do regulamento esse ano, no início do ano, com a antena, ela irá funcionar mais 10 anos. E foi bacana, são realmente 4 macacos que levantaram esses 42 toneladas. Quem?
42 toneladas
É. E aqui tem trilhos, com os macacos baixa, você está a área livre para trocar o rolamento. Tá? Tive algumas tarefas feitas na superfície, tanto fotos, que eu sou mostrado na próxima. Ah, desculpa. Isso. Está mostrado aqui. Essas duas superfícies. E a colocação do novo rolamento. Só levantar a pele. Depois tem todo o balão. Claro, tem que calibrar, tem que refazer o modelo de apontamento.
Enquanto estava na troca, ele é desligado. Eu lembro que o rapaz falou que não podia desligar durante a troca do rolamento.
Desligar o quê?
Algum sistema do.
Sim, claro. Sim. Tem que tirar
Aí depois da troca tem que recalibrar de novo a antena.
E depois da troca tem que refazer o modelo de apontamento.
Leva várias horas, né?
Não, levou 2 semanas. Tem que conectar tudo.
Em comparação com as antenas novas, qual é a massa das novas antenas?
Eu acho que são mais leves. Acho que eu tive um número rápido de pessoas. Ela é menor e a ideia é que seja mais leve justamente para
Um outro material,
Para
poder
isso.
ter uma velocidade angular maior.
12 graus por e a ideia é fazer mais fontes do que esse daqui. Mas o bom é que ficarão, como foram 2 anos funcionando ambas, tá? E depois a outra espero que a gente possa usar tipos, frequências importantes.
Na mesma banda, na 10
A nova banda incluirá essas 2 bandas, vai ser larga banda lá, 2 a 14. E isso que faz com que a nova seja extremamente mais sensível. Então, além de ser mais ágil, ela vai ser capaz de observar fontes extremamente fracas, que provavelmente não estamos detectando nesse momento.
Vai ser menor, porque esse aqui é de 14, né? A outra é de 12. Ah, não.
Tamanho, 12 metros. Bom, isso daqui. Bom, esse daqui é o evento que está acontecendo agora. Só lembrando, né, que eu espero que seja possível repetir essa experiência, que é muito bem sucedida, de enviar alunos, eu vejo daqui, não era aluno, acho que era aluno era doutorando, e por nós lá, para eles treinarem, justamente para dar embora. Deve também, que é esse programa de programação já providenciando algumas dessas matérias de princípio de autonomia. Temos processos. Aqui é importante lembrar-se de está faltando pontos do hemisfério sul, daí a importância
A nova antena.
da nova antena, e deu a antena e a NASA obviamente está muito interessada, não só pelo objetivo científico de Geodésia, mas também pela qualidade esse tipo de relatório que a gente envia cada ano e o retorno da NASA. Obviamente, isso era antes da antena parar. Mas a Fortaleza é uma das antenas que mais pressão em termos de observação, mais observa. E acima disso, não são reconhecidas também. Tanto que, aliás, em 2022, o OE foi homenageado tem uma importante contribuição do observatório ao último modelo ITRF 2020. Então, isso foi uma homenagem do ANS, International ANS. E, finalmente, o novo projeto, aqui muito resumido, de cada um desses aqui é o projeto em si, que foi feito pela KBF, uma empresa norte-americana, contratada pela NASA, que montou esse projeto com a ajuda da gente. A gente fez tudo sondagem técnico, perto do lugar onde está atual, não vai estar lá, tem que fazer acesso, tem que propor o estacionamento, tem que abrir uma porta, para a possa entrar no observatório. Aqui uma imagem de 360 graus, que vai ter as árvores lá. Tem todo um processo de licenciamento ambiental. Nada foi feito de 25 anos, na época não nada de licenciamento ambiental, hoje em dia, claro. Comunicações, inclusive, novo gerador, uma reforma do plano aqui. Precisaremos de outra sala para a nova referência de tempo e as outras. Então, a gente espera em 2024 para uma operação já em 2025. Para isso, eu acho que eu queria mostrar. Acho que isso.
Esse canal do YouTube,
Esse
canal do YouTube,
se eu não me engano, tinha um vídeo acelerado, desenvolvimento da antena, mas eu repasso depois. Toda uma série que na época tinha uma câmara no lugar civil, toda a operação. Basicamente isso.
Okay, thanks. Let me go back to doing another presentation. So the people that are online, I wanted to remind them that we're actually going to have some lectures and more material this afternoon. In the original plan, we were going to go out to the antenna again today, but we're not going to do that. We're going to come back after lunch and then have some more stuff. Right now, I am going to give another presentation, then we're going to break for coffee break, and then we're going to have a presentation on EOP by some of our students. Can people see my screen? Yeah.
1 second, teacher. You need to open a presentation and select that.
Okay.
Is that
That's a presentation. Yeah.
working? Share this tab. It's now sharing. You can use F11. Key.
Yeah.
No, FN.
You do it.
uma função também. Pequena função.
Not working your function.
Let me try going to another browser. This is.
You need the link.
Yeah, but I can keep that up, right?
Copy the link and select another browser.
Let me just see if it's going to work.
Right click.
Right button.
But now the page up, page down isn't working. Okay. this is from the BLBI the BLBI school that happened a couple of years ago in Helsinki. And this is presentation by Patrick Charlot. Patrick is a astronomer at the University of Bordeaux, and the University of Bordeaux, or the Bordeaux University, is where they have this IBS Live, which we saw the other day. And Patrick has some nice pictures of sources, and he's done a lot of work on sources. So I wanted to just go through his presentation. And he talks about a lot of the stuff we've seen before, but maybe worth seeing again. So he's an introduction, and then he's going to talk about what our sources are. I call these sources quasars because that is what I grew up calling them. Quasar stands for quasi-stellar radio object or something like that. And they were named that before they had a good idea of what they are. Now they call them active galactic nuclei. And what these sources are black holes at the center of galaxies. So we have electromagnetism as you have two types. You have continuous emission, and then you have spectral line. And the stuff that we see is continuous emission. We don't really see spectral lines in what we're doing. And here is a pretty picture of various kinds of objects you can study in astronomy. And the stuff that we study are these extragalactic objects down here. When I was in college, I don't know what you do here, but when I was in college, as your last year, you have to do a project or a report on something, or a thesis on something. And I did mine on pulsars.
Professor, with this data, we can calculate the metallicity of stars?
I don't know. So who knows what a pulsar is?
You don't know what a pulsar is?
Who knows what a pulsar is? No, I'm asking. So, I mean, the current idea is a pulsar is basically a neutron star that's spinning. And it has some kind of beam, and we see the beam every time it hits us.
Are we pretty sure that neutron stars are often neutron stars and does not emit radiation?
I don't know. I don't. This is what I was taught. So active galactic nuclei. Radio sources are quasars. So here is a brief history of AGNs. So 3C273 is a source that we still observe, and it's a very strong source. It was the most distant known object in the galaxy at the time it was observed. It was also really, really strong. Stronger, the radio emission is stronger than some galaxies combined. And here's a chart showing the distance. So they measured the distance of these things by redshifts. And the higher the redshift, the further away they are. So who knows what redshift is? Anybody? What's redshift?
Redshift.
It's a shifting of the spectrum proportional to the receding velocity of an astronomical object emit radiation.
Yeah, it's basically Doppler shift. So the object is going away, some light is downshifted. And if we have an expanding universe, the further away something is, the faster it's going. And here is a chart just showing what the distribution is of this, the frequency distribution.
Do you know why just 15 to 20% of AGN are running along?
I do not know.
We don't know why.
I do not know. This is outside of my area of expertise. Now, one of the things about these AGNs is that the strength varies over time, and it varies over lots of different time scales. So these charts are the flux of some sources, and my bet is this probably came from RBLBI data. You can see how sometimes the strength goes up and sometimes it goes down. And at Goddard, one of the things we do is we produce tables every month that give our best estimates of the strength of all the sources that we observe. And then that's used in scheduling things. So there's always some kind of lag between what the real source is doing and how we're scheduling it. And at minimum, the lag is on the order of a month because we update the model once a month. So there you can see variation over years, but you can also see variation over months and variation over hours. And what happens if you use the wrong model? Well, if the source is stronger than you think, all that's going to happen is you have increased SNR. So, you're sort of wasting observing time. On the other hand, if the source is weaker than you think, there's a chance that you lose the source. So when we schedule things, we try to be pessimistic. And the correlators like to have SNRs on the order of 10, but when we schedule with SNRs on the order of 20 as a margin of safety.
Professor, have velocity in 2 times, right?
Pardon?
Have velocity in 2 times in the graphic.
I have what velocity?
Oh, in breaking parts.
I'm not following what you're saying, Max.
But
A intensidade variando
in
espalhadas.
parts and breaking.
You're saying there's no points.
Yes.
We just don't have data there.
Okay.
So
It's not that it's not the case that the science is for a
no,
while.
no. We have finite resources. So here's just a point that Patrick is making is that you can get some idea of the time scale of phrases. The variability of an object is related to how large it is. If you have a large object, you don't expect there to be a lot of variability because different parts of the object, if you have a lot of variability, what that means is you have things changing simultaneously. And if you have a large object, things shouldn't change simultaneously.
That's why we know the size of quasars.
I don't know. I don't know. Here is a picture that comes from the Bordeaux. Bordeaux has this database of sources, and there are lots and lots of pictures here. And there are a few pictures which are circled in green. There's one, and there's one. And for these, you can call them point-like, or you can model them as some sort of elliptical source. So these are good sources. Then there are other sources that have more structure. And you have these ones which are, and they have sort of a point-like center, but then they have stuff that's happening to the side. And then you also have some sort of bad sources. There's really sort of a continuum of these. We have a list of about 300 good sources that we observe. Now, one of the questions that you have, all of these sources, or many of these sources, are part of a celestial reference frame. And if you have an object which is extended and you give its coordinates, the question is, what are you referring the coordinates to? And if I have something that is like that, nice and symmetrical, then you're referring to that point. If I have something like this, it's more problematic. What is the coordinate of it? And what's also an issue with something like this is the structure changes over time. So right now I have a hot spot there, but maybe the hot spot will rotate down there. So I can have changes in the apparent source position just because the structure is changing. So in VLBI, our measurement, or what we actually use is the delay. And here he goes from the image of the source as a contour map into variations in delay as you have different antenna spacings. And what you want is, you want no variation in the delay. So that's the maps downstairs. You want those to all be gray. And as you have more and more structure, you get more and more variation as you go across like that. So what this shows up with is noise in our measurements. And there's some work being done by some people in Europe and also my colleague Sergey Boletin on how do you model this. One motivation for modeling this is all sources have structure. So, even our nice sources have the potential to become non-nice. And secondly, some of the strongest sources have structure. So the main thing we do now is we try to observe good sources. Most of our sessions have some number of bad sources to sort of monitor what they're doing. And the thought that future on we can figure out how to handle them correctly. I mentioned previously that several times we've had these campaigns which last for 2 weeks, where we observe the same set of stations over this 2-week period. And these con sessions can also be good laboratories to test modeling sources, because you can try to model a source in the first session and then see if you can use a model going forward. So here is a picture showing the time evolution of some sources. And you can see that on this side over here, we have good sources where you don't have a lot of time evolution. And here you have a bad source where it's has this jet that's coming out and it's changing over time. Now, one of the things that sometimes happens with these things here is that when you're observing it, sometimes the correlator will pick up this as a peak, and sometimes it will pick up this as a peak. So sometimes the measurements, when you're processing it, will have, it looks like you have 2 sources, when really you have an extended source. And one of the things that happens is that the apparent position of the torsion changes over time. And here's some examples of that, where we're just plotting the right ascension and declination as a function of time. I should mention that back in around 2005 or so, somebody discovered that some of the sources that we were using a lot, their position varied, and it was corrupting our data. So we had to go back and say, exclude this from when we were doing routine analysis. Now Patrick talks a little bit about the ICRF3. This is the International Celestial Reference Frame 3. And what you want to do is you want to have some set of sources to define the celestial reference frame. And this serves as the counterpart of having geodetic markers on the ground. Now, I don't know if we saw any when we went out to the station, if there are geodetic markers there, but sometimes, even if you're just wandering around on the streets, you can see a surveying marker, which is like a brass marker on the ground, and that serves as a reference point. And so sources serve as exactly the same thing. They serve as reference points in the sky. And although I haven't talked about it here, NASA uses the celestial reference frame to do spacecraft navigation. and they do VLBI, where they look at the spacecraft and then look at a nearby source. And they look at the spacecraft and they look at a nearby source. This helps us determine the position of the spacecraft. And VLBI gives you, when you do that, you get an angular measurement, whereas things like radar just give you a distance measurement. So, back in the 1990s, there was a spacecraft that crashed into Mars.
Yeah.
And do you know why it crashed into Mars? Does it?
In metric in the calculation of everything.
Yeah, so it's one of the rockets, the company that sold the rockets, they gave the thrust in like foot-pounds.
Yeah.
And NASA assumed that it was in newtons or whatever. So, yeah. And so ever since then, JPL has been very careful about making measurements correctly. And I'll tell you that after that happened, NASA passed a regulation saying everything had to be quoted in metric units. Congress passed a law overturning that. So, I'm not sure what the current status is. So here is just a picture, a schematic diagram of what we have. You have this black hole there in the center, and it's rotating, which is why you have this disk, and then you have these jets coming out. And here is a couple of pictures of jets, and conceptually, I don't quite understand how this one works. This is supposed to be where the jet is like in the plane of the sky, so I'm not quite sure why you see two of these things, but here is where the jet is coming sort of towards you, where you see this long plume. Now, one of the things I think that Patrick is going to talk about in the next slide or two is that this jet looks different at different frequencies. And one of the things that was observed about these things is, these things that have two components. Start down here in 1998, you have this big component, then you have this other component. The other component is going away. And it looks like this is apparent faster than light motion. But it's not, it's just some geometrical effect. So, dichotomy, radio loud, radio quiet. So I don't really know enough about this to talk about this. But here's where I was talking about jet properties, that you have the black hole here and that you have a jet coming out here. And depending on which frequency you're observing at, you see different parts of the jet, because different parts of the jet are higher or hotter at different frequencies. So now he talks a little bit about our observables in imaging. And in geodesy, what we use is the group delay. And that's primarily what we're interested in. In astronomy, they're interested in making pictures. And their measurements are the amplitude and phase. And when you have these pair of antennas, each pair of antennas, one of the things they can measure, they do the correlation process, is the amplitude and the phase of the signal, of the cross correlation. And if you look at an image of the objects on the sky, it is there's a relationship between the Fourier transform of the image and what you receive at the radio antennas. And just take my word on it. So if you look at the radio antennas, you receive some signal, and then if you do the Fourier transform, you get the image of the object. And the amplitude and the phase provides us with different kinds of information. The amplitude tells us how much a certain signal is. And the phase information tells us where the image is located. So in the next chart I'm going to show you, the phase is going to change. And what's going to happen is that the only thing that's changing is that these positions are changing. So when you do the Fourier transform, it shifts the phase. So here's an example of, this image has changed. See that? If I just go back and forth. Okay. So amplitude tells you how much, phase tells you where the component is located. So I think somebody asked, suppose we have lots of small antennas. Well, you can do that. And there's this array of antennas in, where it's in South America, where they have this array of antennas to do radio telescope, to do radio astronomy. There's a couple of other things. So that's sort of the ideal case. And in real life, well, one thing you have is, if you want to have really small resolution, you need the antenna, you need to have a big array. So it would be impractical to have an array like this cover the world.
Professor, what's the diameter of one of that antenna?
You choose. This is fictional. So in practice, what you really do is you have some array of antennas on the ground, and then they observe. And if I look at this, I have these circles here. And what these circles are is these antennas are observing some source, the same source over time, and the Earth is rotating, which is causing those circles there. And, when you're doing the Fourier transform, ideally what you'd like data that's evenly spaced. You'd like the data to be gridded. And in fact, you don't have that. The data is irregularly spaced. And when you do the Fourier transform initially, you get something that looks like this. So you get something that looks like the image, but then there's lots and lots of other stuff. And these other things are artifacts of how you do the sampling. Now, it turns out that, this Fourier transform stuff is also used in things like medical imaging. And, in medical imaging, they have the same sort of issues, and they use a lot of the same sort of techniques as we do. Okay, so Patrick is just going through the details. There's a process called cleaning where you do an iterative solution. You start with one solution, and then you iteratively get rid of components. So and you end up with this clean map. So you take a solution, you Fourier transform it, you get something, then you discard stuff that you think is unrealistic, you Fourier transform it back, and make sure that that's consistent with your data, and you just go back and forth, back and forth. So here's a picture of a model, and then this is the dirty beam. The dirty beam is your effective antenna pattern you get from this array of things, this dirty image, and then the clean image. So this is after doing all this processing. Okay, I don't understand this well enough to say anything. There are several software packages. There's APES. And APES was written in the 80s and 90s. And That's sort of the old software. There is a replacement for apes called CASA. CASA used to be called apes++, because there's a project starting in the 1990s to rewrite apes in C++. So that was renamed to CASA. And then there is this other thing called DiffMap. The DiffMap is software that is only used for making images.
GitMap.
DiffMap.
DiffMap.
DiffMap, yeah.
They are all open source.
They're all open, so they're all free. They're all free. What one of the issues is that making maps is currently time consuming, and so people are looking at ways of making this faster. Maybe if you start with an a priori map, you can make it faster. And here's just some acknowledgements. So, okay, so now we're going to break for coffee, and we'll come back at 25 seconds.
Okay.
I'm going to give a very brief, show some baseline graphs, and then I'm going to give a presentation, and then we'll have lunch. And yesterday, I showed some plots with Fortaleza, and we had nice smooth lines. Today, I'm going to show some plots with Tigo Concepcion. So this is a VLBI site that was in Concepcion, and there was an earthquake there. And
That's when
pardon? Yes, that's when we. So it happened in 2008, and you can see that there's a jump of, here you can see it's like almost 2 meters in the position between Hartrio and Tigo. And there's a couple of things to note here. One is that the response after the earthquake is different than it is before. You have this curvature there, and the slope is still not what it is prior. So there's some anelastic deformation going on. So that's something that you have to model. And the ITURF 2020 includes models of this post-seismic deformation. And the models are based on both VLBI data and GPS data. So here's this Tigo thing. And this is one of the reasons when we did the computer the scatter yesterday, we saw these huge results for baselines involving Tigo, because we included data from here and data from there. So that's one baseline. Here's another baseline, same sort of thing. Another baseline, another baseline. And in this baseline, you can see that things are opposite sign, and the reason they're opposite sign is because
Break time, right?
pardon?
Break time or not?
Break time? I'm not sure.
The jumping in the data.
The jump in the data is from the earthquake up here. So, I think this is interesting data. And then here we had a case where we had a between Tigo and Tsukuba. So Tigo had an earthquake in 2008, and in Japan there was this earthquake in 2011. So there's this brief period of time when it sort of settled down. Then we had this earthquake in Japan, and so that's all. I wanted to show you this stuff so that you got a feeling for it. Okay, now I'm going to go to another slide, another presentation. Do I have to do anything?
Is that?
Yeah, that's it. So it turns out that our students were not able to do a presentation on EOP. So I gave a presentation on EOP to the Naval Observatory the day before I came here on the history of EOP measured by VLBI. So I'm going to give this presentation here, and then we'll break for lunch after that. So some of this stuff I will skip over because I've already done it. Okay, that's working. So here's just an agenda. I'm not going to talk about what EOP is very much because we've already talked about it a lot. But here is sort of the standard slide we use. EOP has these 5 components, or 3 components. There's nutation precession, which is the orientation of the spin axis. Then there is polar motion, which is where the spin axis is on the Earth's surface, and then there's UT1, which is the rotation around the spin axis. And there's some excellent videos here that you can do that give you a good feeling for what's happening. And DUT1, UT1 is an angle. It's how far the Earth is rotated. If we take the time derivative of that, we get a rotation rate. And that's related to the length of day. So the derivative of UT1 is basically changes in the length of day.
Can we go back one second?
And we also have derivatives of polar motion, but they don't have a nice explanation or something that's intuitive for us. So why is EOP important? Well, scientifically it's important because its changes in it are due to changes in angular momentum or exchange of angular momentum or torques, forces caused by the sun and the moon and the planets. And so by studying EOP, by measuring EOP, we can get a handle on these forces. And I asked Professor Martin to bring in 2 eggs. One of these is hard-boiled and one is raw. And you can easily tell which one is which by spinning. So when I'm done with the lecture, you can come up here and do it. I pass it around, but I don't want you to drop my lunch. And so technically, we need to know EOP to point antennas and to calibrate GPS orbits. So that's one of the reasons that VLBI is supported, is to measure EOP. And in the US, the VLBI effort is supported half by the Defense Department and half by NASA. Polar motion is the location of the spin axis on the Earth's surface. And here is a plot of x-pole, polar motion. And it has this nice up and down sinusoidal variation. And you can see sometimes the period gets bigger and sometimes it gets smaller. And the reason is there are actually 2 periods. One is a 365-day period, which is seasonal, and that's related to storms and stuff that's happening in the atmosphere. And then there's a 435-day period, which is called the Chandler Wobble. It's called the Chandler Wobble because it was first sort of discovered by Chandler. It was actually predicted by Euler, and it is due to the fact that the Earth is an ellipsoid. Now, in the States, we play baseball and we play softball. So I don't know what the dimensions of soccer field are, but, huh?
100 or what?
No, the ball.
No, not the ball. The spot of the field.
It's like no, it's we want to know the diameter of the football.
Yeah, I'm interested in the size of the field.
The field, 100 yards.
100 yards.
9 to 100 yards.
And how wide is it?
70. Not 40 yards. 30 to 40 yards.
30 to 40 yards.
Yeah.
Okay, so in this variation here, if you put it on the Earth, it's about 15 meters, 15 or 20 meters. So it's this basically goes this big circle around like 15 to 20 meters, and this chart here shows polar motion x and y, and then variation over time. So that's what it is. And I should mention this thing here is most of my charts are with respect to year 0, with respect to year 2000, which is when VLBI started.
It was electromagnetic signal. I would say that it's heavily populated.
You'd see that signal? Yeah. So here is UT1 measured by VLBI. And you can see that the angle is steadily decreasing, meaning that the Earth is slowing down. Except for if I look at the last bit, then it's changing. And UT1 it started to decrease, starting in about 2020, and it's continued. And the thought is that's due to changes in the shape of the Earth caused by things like the glaciers melting. So you have a redistribution of mass. And this is LOD, which is just a derivative of UT1. And this is all VLBI measurements going over the last 40 years. And in some places you can clearly see the strong seasonal term. But in some places you can see a strong peak. And that is due to an El Nino event. And there are other places here where you can sort of see that as well. And here is just the seasonal dependence of LOD over a couple of year span. And if you look at it, it's peak to peak, it's roughly 1,000 microseconds or a millisecond.
Right?
Yes. And so what I did was I took this data and then I just took the average value over 365 days. And so you see that variation there, and that is due to seasonal effects. It's due to so the Earth, the day is longer in northern hemisphere winter, or southern hemisphere summer. And the reason is because you have more angular momentum in the atmosphere, and the conservation of angular momentum means that the Earth has to slow down to compensate. And you can decompose UT1 at all time scales. So there's, here's a plot going back 30 years or so. And you have this like long-term variation, decadal variation, you have interannual variation, seasonal, interseasonal, etc. So there's stuff happening at all time scales.
So regular.
They're lying. I mean, it's just an illustration.
Oh.
So if I look at a spectrum, I can do a spectrum. Look at something like this, and you see seasonal terms which are pretty pronounced, but then you have some ones that are very pronounced, and those are tidal terms. And that's due to, and the tidal terms are primarily monthly and fortnightly and related to the moon. So that's caused by variation. The moon causes changes in the Earth's tide, and that influences the Earth. So those are the tidal terms. If I get rid of the tidal terms and the annual terms and the seasonal terms, then I have something like this. And Jean-Pierre showed this plot earlier. I probably showed it earlier too. And what I'm plotting here is, in blue, the LOD, residual LOD, after subtracting all of this stuff. And the red is something called the modified El Nino index. And that is a measure of how strong the El Nino is. So if you look at one of the things that happens when you have a strong El Nino is the Earth slows down. It slows down. Yes, the Earth slows down, and the actual idea is you gain about 1/10 of a second in time. And then when, the first time I gave these talks, the Earth slows down, you gain about 1/10 of a second in time, but don't squander it, because when the El Nino goes away, it goes back to normal. And here's a chart showing sub-daily variation. So this is also due to tides, and it's the fact that I have these daily tides, and the water sloshes back and forth, and it causes the Earth to, change its rotation. And this is one of those things that we looked at where we said, suppose I remove the subdaily variation from EOP data, what do I get? And what this plots here is, it's hourly estimates from BLBI is a blue versus the model. You can see that the hourly estimates and the model estimates agree very well. There's some residual signal, and it might be noise or whatever, but in any case, the model is very good. So I want to take a look back at a longer picture and talk about evidence of changes in the length of day over a long time period. And there are some people who have looked at fossils, and what they've done is they've counted the rings in these fossils. And this is a sediment. And by counting the rings in the fossils, the rings are due to deposits of minerals on sedimentary rocks that end up turning into rocks. You can count the rings, and you can figure out how many days there are in a year. And for this particular fossil, we found there were 486 days in a year. And so this is one particular one. There are lots and lots of other things. So they gave a reference to here. But here's a chart where folks looked at lots of different fossils over time. And this shows what the length of day is going back 900,000 years. So 900,000 years ago, one day was only 18 hours long. So the Earth has been slowing down over time. And this is from fossil evidence. You also have evidence of this from the historic record, and you can do that by looking at eclipses. So here is a chart where there was an eclipse that happened in Babylon in like 300 BC. And in Babylon, it was a total eclipse. But if you just predict where the eclipse should have happened, if the Earth had been rotating at a constant rate, it actually would have happened over the Western Mediterranean. And that corresponds to a difference in time of 12,000 seconds. So, that's due to the fact that the Earth has been slowing down over time. And people have looked at various historical eclipses over time. And, and that chart over there shows sort of the slowdown of the Earth based on measurements of eclipses in history. So to find something like this, first off, you have to know that an eclipse happened. And scientists generally, I don't know eclipses happened in Babylon, so I went to a talk by this guy, and this guy said, basically, he appealed to any historians. If there are any historians and you knew about an eclipse, then let us know. And then you have to figure out the time and know how good the time records were. Because back in Babylon, 1,200 seconds is a pretty long time.
100 minutes.
12,000 is, that's 200 minutes. Yeah, so it's like 3 hours. So the further back in time, the better you are. In any case, so there are sort of practical obstacles. So people looked at eclipses in Babylon, in China, and other places. And if you want to read this paper, you can get more evidence there. So I just showed you that the Earth has been slowing down. I've given some historical arguments for this. And the reason it's slowing down is something called tidal friction. Has anybody heard of tidal friction before? Okay, so I think it's an interesting argument, and it's pretty easy to understand. So here I have a picture of the moon, and I have a picture of the Earth. And our naive picture of the Earth is that it's this ball. But really, when I have the moon there, the Earth is distorted. The part of the Earth that's nearest the moon is 40 centimeters up, and the part of the Earth that's furthest from the moon is 40 centimeters away. So I have this bulge caused by the moon. Now, that happens if the moon was just directly over the Earth, but that's not the case. The Earth is actually rotating, and the Earth is rotating faster than the moon is rotating, is orbiting. So what I really have is that the bulge is ahead of where the moon is. And that causes a torque. The moon is attracted to those two torques, and it's trying to pull the Earth back. And at the same time, the Earth is, those two bulges are pulling the moon, and it's trying to pull the moon forward. So the net effect is the moon's orbit is going to speed up, and the Earth's orbit is going to slow down. And at some stage, the Earth and the moon will be in perfect sync. And at that time, one day will be the equivalent of 50 days now. So this sort of effect you have everywhere. And that's one of the reasons that the inner planets, Mercury, they always have one face towards the sun. Yeah, they're tidally locked. Okay, so I don't expect you guys to know what this is, because the people at USNO didn't know what this is, and they should. But this is one of the first geodetic networks, maybe the first geodetic networks. And this is called the International Latitude Service. And they had a set of 6 observatories, all at the same latitude. And one of them just happens to be 10 miles from where I live. And this observatories all measured where some stars were using optical measurements. They had a set of like a dozen stars or a dozen groups of stars. And so every night they measured where these stars were. And here's just a history of this latitude service. And the reason they were doing this was they wanted to see if the Chandler wobble was real. So Seth Chandler had predicted it, so they made these measurements, and the service ran for almost 100 years. And later on, it was renamed to Polar Motion Service, because that's what they're measuring. And then it became part of the IERS, the International Earth Rotation Service. There used to be 2 different services. One, the Polar Motion Service, which reported polar motion. And there was another one called the BIH, which is French for Bureau International Time or something. And those were merged into the International Earth Rotation Service. So that's just some history. Nope. Okay. Here is a chart showing the accuracy of Earth orientation measurements as a history of time. And you see that huge decrease in formal errors, increase in accuracy. And this is due entirely to VLBI. Our first VLBI measurement came on in 1979, and then we had a few measurements after that, and then we started to have regular measurements starting in about 1984. So I have the UT1 sigma, and then I have the X sigma. And yes.
The peaks in 2004, 6, and why is that?
I do not know, and I took this there. This is from the IPRS, and I don't see those peaks in my data. So I'm not sure exactly what they do. The IARS is responsible for making a series, and this is from them. But I don't believe those peaks there. Here is VLBI. I don't know, but you keep 1,000 times, yes. And here are 2 of our favorite antennas, Cookie and Betzel. So these have both been observing a long time. I'm not going to say a lot about it or about this. And this is the IBS and cooperating.
There's a station in
There are 2 stations in Antarctica. Yes.
American ones, Canadian,
Now, one is Chilean, and
Higgins.
the O'Higgins, yeah, and the other one is Japanese. That's soy. So the one in O'Higgins is it's operated by the Germans, but it's on a small Chilean military base there. And they send down Germans there to, man the antenna sometimes or take data there. And there are a couple of things about it. One is it takes they only get the data back like twice a year. Yeah. And one of the Germans who went down there says that every morning, all the Chileans officers stand outside and they play this Chilean national anthem. And they all put their, do whatever the Chileans do. And then they play the German national anthem.
With the Starlink, we can get the data every day now. Because you don't need to take the HD and transport to somewhere.
I don't know how expensive it would be.
Starlink is
Yeah, that's the devil.
So we can rarely compare Higgins to in the scan. You can't show. I want data from Higgins in my scan.
Yeah, there's special sessions devoted to O'Higgins. And if you look at the master file, they'll say like O'Higo 1, O'Higo 2 or something. And so those sessions, the sessions involving O'Higgins and Soya are just for the terrestrial reference frame. As I said, the data comes back at a long time. And at Goddard, periodically we review the data to see what sessions have not been correlated yet. And it's always O'Higgins, which is
There's no, but they don't have internet.
no. I mean, they don't have, yeah. I mean, they must have internet, but they don't have cables or anything.
Mas better, internet would be better than to physically transport
Yeah.
data.
Yeah.
Teacher will first.
So this was this, what caused the peaks in the observation precision graph? And the answer is, I don't know. I didn't make that data, and I don't see that in the VLBI data, so I'm not sure what it is. Could be an artifact. Okay, so this is VLBI. We've seen this a lot. And then I talk about the effect of the rotation of the VLBI delay. And so it may be worthwhile going through this a little bit. If I have an infinitesimal transformation of a network, it's of the baseline. The baseline goes to itself, then it goes to a piece which is proportional to the cross product of the rotation times the spectrum. So I'm not sure if anybody's seen this, but that's what happens. So if I have a rotation on the z-axis, the baseline is xy, it rotates. And this causes a small change in the delay of that. And this has a maximum effect if the rotation is perpendicular to the baseline and perpendicular to the source. So how to see that is that if I have a baseline like this, and I have a source out here, and I have a rotation around this axis, nothing happens. But if I have a rotation like this, I get, if I have a rotation like this, also nothing happens. But if I have a rotation like this, then I have a large effect. So here's just what I was saying. And one of the things to note is that the change in the delay is proportional to the baseline delay. The longer the baseline, the bigger the change. So if you're interested in measuring UT1, which is rotation about the z-axis, you want to have a baseline that's long in the east-west plane. And if you're interested in x-pole, you want to have a baseline that's long in the xz plane. And conversely at the bottom. Okay. So now I'm going to talk about measurement of EOP with 24-hour sessions. And regular measurements of EOP started in 1980. And different groups organized them. And we had different campaigns for different series that lasted for different periods of time. And the first one was called Polaris, and it was small networks, two to four stations at a time, and they ran once a week. And then we had a slightly increase in the size, and it ran 5 times a week. Irises. There are also some other measurements. Iris S, which included, the S stands for Southern Hemisphere, so they included stations in the Southern Hemisphere, and those ran monthly. And you can go through and see where we are right now. Right now, we have 2 EOP measurements a week, one that runs on Monday, that's the R1s, and one that runs on Thursday, the R4s. And NASA is responsible for scheduling one of these, and USNO is responsible for scheduling the other one. One of the things I want to mention is that when I first started in Build BI, it was about 1986, and they had software where they took these iris measurements, which were at every 5 days, and then they interpolated between them. And when they went to doing it, they had software that went from every 7 days and interpreted. And then the cadence, the frequency changed to 5 days. The software was broken. So my very first task at DLBI was write software that used EOP at 5 days instead of at 7 days. And what I ended up doing was writing a Kalman filter to take all the DLBI data at arbitrary spacing and then get daily values. And you still use this program to this day.
What was the language for that?
It's Fortran, yeah.
19, no, that was 86. And it was not 94.
It was Fortran 77. And yeah. One of the issues is that a lot of our code is written in Fortran, and a lot of it is written in really, really old Fortran. So some of our code is written before they had character arrays. So they use something called tolerance. Okay, so the other thing to note here is the cadence has increased, but the network size has increased.
Don't get me wrong, the libraries in Fortran are used to say clean bus.
Yeah, blast. But yeah. And that's used in Python, although people don't know about it, right? It serves as a
those test.
Yes, they work. So here's a chart showing the different networks over time, and you can see that the size of the network and the number of stations has increased. So, because of this, our EOP has increased. The precision of the EOP has increased. And here is a chart where I just show for each EOP session that we've done, how many stations we're involved in. And you see some peaks over here, like that, or like that, or like that. And those are special sessions. Those are some of our cont sessions where we had large networks that observed for 2 weeks to determine state of the art. So here is a chart that shows the UT1 formal errors over time. And this is a log scale. So the bottom envelope has been decreasing pretty rapidly. And then if you look around here, it looks like it's increasing. And we first saw this back 10 years ago. And at that point, it decreased to there, and then it started to increase. And this is sort of an artifact of the reference frame. And the reason is that part of the uncertainty in UT1 is the uncertainty in the reference frame. And if you look at the reference frame is most precisely determined, not now, but sometime back from now. And the analogy for this is if I'm fitting for a straight line, the place where I know the value the best is not at the end points, but it's someplace in the middle. So, this is sort of, as I said, but in any case, our best precision is a couple of microseconds in UT1. And here's the same sort of thing in polar motion. And the units here are different. They are in micro arc seconds. Okay. So, how large is the uncertainty? And usually we quote UT1 in seconds or in microseconds, and polar motion in micro arc seconds. And this is historical because we tend to think of polar motion as an angle and UT1 as the time. And here's the conversion factor from millimeters to seconds for UT1. And if I look at here, I have this nice even number there, 40,000 kilometers. Does anybody know where this number comes from? So why is it 40,000 kilometers? I think I may have already said this before, but it was defined as 40,000 kilometers. The Academy of Science in Paris, when they invented the metric system, said that the distance between the North Pole and the equator and the meridian passing through Paris was 10,000 kilometers. So it makes it easy to remember. So you have this 1 millimeter precision. It's about 2 microseconds or about 30 micro arc seconds. Here are these quant campaigns I mentioned. Every 3 years, we've been having a quant campaign. The earlier ones were, I think our first one was like quant 92. And you can see the network size has been generally increasing. Quant 17, the network isn't as big as quant 14 because we split the network into 2. And in quant 17, here are the 2 networks that we had. And the red one, most of it is a VLBA, but then we had some non-VLBA station. And the blue one is other station. So the blue one, I think, is better globally distributed than the red one is. During Con 17 was also the first sort of demonstration of the BIGOS system. And these were the antennas that were supposed to participate. Onslow and Hobart, their hardware was not ready. So we had this line of stations up here. And one of the characteristics of this is it's all on about the same latitude. So unfortunately, that means that some of the components of VOP are not well determined. So one of the things that you can do is, if you have 2 independent networks, is you can compare the measurements of the 2 networks. And this gives you an idea of how precise the networks are. So here I'm comparing X pole and Y pole. And there's an offset of 45 microseconds, which is due to the networks being slightly misaligned. But the scatter is about 50 microseconds, micro arc seconds. So that gives you some idea of the precision of these. And I can also look at UT1. And here there's a generally good agreement. There's a couple of points that are outliers. But the agreement between the 2 networks is an RMS of 4 microseconds. So anytime you're dealing with a technique that is very precise, one of the issues is, how do you know how precise it really is? And here's one way of doing it, is to compare measurements, independent measurements made by the same technique. Another alternative is to compare it with measurements made by GPS. And GPS can't measure UT1, but GPS can measure polar motion. So here is a chart showing measurements, the difference between VLBI and GPS measurements of polar motion. These points here are R1s and R4s, which are our regular EOP measurements, and over here are the CONT measurements. So you can see that the scatter is generally smaller here than it is over here. So one of these is for X pole and one is for Y pole. So here is a summary showing what the scatter is between VLBI and GPS, so the IGS results for the different comp campaigns. And you can see here that our best agreement occurred during Con 14 when we had the largest network. And in Legacy 1 and Legacy 2, the agreement was not as good. Legacy 2 was worse. And the reason Legacy 2 was worse is because of the distribution. That's the one which is mostly concentrated in North America, that has some stations in it. Okay. Now I'm going to spend the last like 5 minutes or 10 minutes talking about UT1 measurements. And UT1 is rapidly degrades with time. And here's a formula. The degradation in time is about 35 microseconds times t to the 3 halves. And here's a plot of it. See that when you get out to about 1 week, your measurement is degraded up to, the uncertainty is 6 microseconds. So you want to have the data as fast as you can. And how do you go about doing that? Well, you have a couple of things. One is, to get good UT1, you need to have long baselines. And to reduce the data, you need to get the data to the correlator quickly. So that means that you want to have a session that is short, and you want to have long east-west baselines, and you want to have a small network. So here is this Cookie-Betzel baseline, one orientation. And here is another orientation. And here is a chart showing typical sky coverage at Cocaine. So this chart here shows this big circle here is the part of the sky that's visible at Cocaine, but only part of that sky is also visible at Betzel. And that's this part there. So this is the only part of the sky that you can actually observe in. And here are measurements from a typical intensive. And we have 23 scans.
Why that formula for the delay in the it is just a coincidence that it's very similar to the of Hebrews orbits.
It is. And the reason that you have that formula there is, let me go back to it. This has to do with the stochastic nature of it, and this 3/2 power law often appears in formulas having to do with random processes. So that's fundamentally it. And at longer time scales, that power law changes, but it has to do with the process that the fact that it's stochastic. And you remember you look at the spectrum, and the spectrum was like down like that, it had this straight line. So there was stuff happening at all time scales. So. Okay, so that's a typical intensive. And so there's some problems with this. And one of them is that the number of sources which are mutually visible is limited because you only have a small slice of the sky. And around 2005, we noticed that during some times of the year, the intensives were bad. They're giving bad numbers. And what it turned out happened was that there are only some sources available that we were observing. So they're like all clumped in one area. And we expanded the source list, and that fixed that problem. Another issue is that since you only have a few sources, if your model for one of the sources is bad, then you can lose many observations. Whereas in a 24-hour session, you have observed 100 sources. If you lose one source, you lose maybe 1 or 2% of the data. And in intensives, you can lose 10 or 20% or 30%. Another issue is that since you only have a few sources or a few observations, it limits what you can estimate. So this means that if you have errors in your a priori, that will go into errors in your UT1 estimates. So one question is, how good are the intensives? And the technique I use to evaluate how good the intensives are is to compare them with the UT1 estimates from 24-hour sessions. And here I have a chart showing my typical week, and I have a 24-hour session here in R1. I have a 24-hour session here in R4. And the epoch of the estimate for the 24-hour session is right in the middle of that. And these intensives here are roughly 12 hours away from the epoch of the estimate, which means that my error in extrapolation is on the order of 2 microseconds. Whereas if I try to extrapolate the UT1 from this to there, my error is on 61 microseconds. So I can't evaluate the accuracy of that. I'm left to evaluating the accuracy of those. And here is a chart that shows the accuracy of the intensives. There are error bars, and see here that the RMS scatter is about 23 microseconds, 22 microseconds. So that gives you some idea of what the accuracy is. Now, I started this section by talking about one of the important effects was latency, and that is how long is it from when the data is taken to when it's lost. And here is a chart showing the latency of intensive measurements over time. And back in the olden days, when we first started doing this, some of them took over 100 days to get the data processed. And as we move to better, over time things have improved. In this epoch, we were shipping stuff by mail or by UPS, and so you can see that the time has decreased. And nowadays we are down here around under a day. So yes.
So the 24-hour sessions was pressure. So if the intensives that are 1 hour take in the old days take this long time, the 24-hour session was possible for.
Well, the 24-hour session would take longer than this. And right now, our 24-hour sessions, the latency is 2 weeks. So the advantage of the 24-hour session is they measure all the components of the EOP, UT1 and polar motion. Whereas the intensives only measure UT1. Now, polar motion changes, but it doesn't change as rapidly. So you can use the values for polar motion, that you get now over the next couple of weeks, and they'll still be okay. Plus, you also get estimates of polar motion from GPS. So the 24-hour sessions are still good. They're used to sort of adjust the series. But really, for UT1, you need 1 hour. So in any case, so here we go down here. We're now sub-daily. A session is taken, the data is shipped to the correlator, and then it's processed. And here is something where I've changed the scale to sort of hours to sort of days to hours. And you can see that most of our intensives, the data is available in under 6 hours. So this is the time from when the session ends to when the data is publicly available. And a large part of this is due to automation. So we've automated a lot of these processes. Some of these things up here are due to the fact that the data comes in at the correlator, and the guys have gone home for the night, or something like that. Well, actually, so that's to the first Vigos DB. Here's the first analysis, signal sort of plot. And I just want to mention that there are other intensives besides Tokyo itself. There is Ishioka, which is a station in Japan, which observes a Betsel, or Mauna Kea sometimes observes a Betsel, etc. And we have intensive measurements every day of the week. And this chart shows when the measurements happen. Here are the normal intensives, so they happen Monday, Tuesday, Wednesday, Thursday. And here's a session that starts on like midnight on one day, or 23:30 on one day, and ends at 30 minutes after midnight on the next day. So the question is, can we improve the accuracy of the intensives? And the only way to improve the accuracy of anything is to have more measurements or lower error. And our new system is supposed to buy us both. So here's just a comparison of the antennas. The new antennas move much faster than the old antennas. They take a lot more data than the old antennas. They're smaller. And here's what the new antennas look like. The antenna at Fortaleza is going to look something like this, because it's the same basically the same manufacturer. Now, here is a comparison of two intensive sessions, one with SX and one with Vigos. And there's a couple of things here. One is that there's this hole in the sky coverage, and that is because the SX antenna blocks the Vigos antenna.
But Vigos is a combination of VLBI and satellites.
No, Vigos is just VLBI.
Just VLBI.
Yeah, yeah. Vigos has these small antennas that observe broadband. I'm going to skip that. So here's a comparison of my Vigos session with my R1, R4 sessions. There's a gap here because there was problems with Betsel or Kokio, one of the antennas. But the important point here is that the scatter is less. It's about 17 microseconds as opposed to 22 microseconds. And here's a comparison of the formal errors of the scatter versus the formal errors. And the formal errors are, how accurate we think the observation should be based on the precision of the individual measurements. And for Vigos, or for SX, the formal errors predict about 12 microseconds. We're actually about twice that. And that means that and the reason for that is unmodeled error, probably the atmosphere. And for Vigos, if the formal errors are 4.4 microseconds, so much smaller, and the accuracy is actually 5. So the last thing here I want to say is that USNO began using Vigos intensives operationally in their product, and that using the Vigos intensives improves their prediction, their DOP products. This happened, I think, earlier this year. Okay, so here's a quick summary that really precise EOP measurements are only made possible with VLBI. VLBI measurements have been increasing slowly and steadily. And our best measurements for UT1 are about 2 microseconds, about 30 microarcseconds for polar motion. This is comparable to what GPS does. GPS does about 30 microseconds for that. GPS cannot measure UT1. So that's one of the reasons we still need UT1. Now, so that's the end of my talk, but it's time for you guys to come up here and tell me, spin these eggs and see which one is which. Yeah, you want to show, are you showing it on the camera? Yeah.
Esse é o cozido, esse é o cru.
Esse é o primeiro.
Não, acho que não. Esse aqui é o cozido. This one's the cooking one.
That's one yes. So, this shows that like external torques can tell you something about what's happening on the inside. So here I have a hard-boiled egg and a raw egg. You can also do a soft-boiled egg, and you can tell the differences between them. And when you had these, earlier I showed you like this nutation stuff that was going along like that. There's a model of what the nutation should be. It was built in the 1970s. And then when VLBI came along, they found out there were deficiencies with the model, that the measurements did not match what was happening in the model. So the nutation model was refined, and there was a new one. And now there's a newer one still, and the newer one includes the effects of gravitational torques by some of the larger planets like Jupiter. So, here's an example of you have feedback between measurement and theory. And that's it. That's it for today. So we'll start at about 2 o'clock.